Okay, in this video we're going to be looking at speed versus time graphs, and we're going to look at specifically focus on calculating the distance travelled from a speed time graph, and we're going to look at different shaped graphs, and we're going to look at describing the motion shown by a speed versus time graph. So let's first of all remember what we mean by speed and acceleration. So speed is defined as the rate of change of distance, and what that means is it's the gradient of a distance versus time graph. And acceleration is the rate of change of speed, and what that means is it's the gradient of a speed versus time graph. And what you can see there are mathematical expressions that communicate exactly what we've just said. So that's the definition of speed and acceleration. Now let's get on to calculating the distance travelled from different shaped speed versus time graphs. Okay, so to get the distance travelled, first we need to rearrange the equation we had earlier. So I'm making the distance travelled the subject of that equation. So what this equation we're now looking at means is that the distance travelled is the area between a speed graph and the time axis. Now I'm going to show you what that looks like now. So say we're asked to calculate the distance travelled by a car travelling at constant speed of 10 meters per second in 20 seconds, and we want our answer in meters. So we saw on the previous slide that to get the distance travelled, we need the area between the graph and the time axis. So the red line is the speed graph. Now we can see the speed stays the same the whole time because it's a constant speed. So the area between the graph and the time axis, therefore, is a rectangle. And we calculate the area of a rectangle by multiplying its sides together. So this rectangle has sides of speed and change in time. So therefore, the distance travelled is the speed times the change in time, which is 10 times 20, which is 200 meters. So this is the simplest type of graph to calculate speed from. So one of the ways of making these simple ones more difficult is adding in a unit conversion, and I'll show you what I mean. So again, we've got constant speed, but this time it's 100 kilometers per hour, and it wants to know the distance traveled in 60 seconds, and we want our answer in meters. So the first thing we need to do is convert our speed into meters per second. So to go from 10 kilometers per hour, we multiply by the number of meters in 1 kilometer, which is 1,000, and then we divide by the number of seconds in an hour, which is 3,600 there. So just to explain what the notation you can see there means. So on the right hand side, ms to the power of -1 is the same as meters per second, but it's just easier to write on the computer, so that's quite commonly used. When you see meters, the unit of meters per kilometer, that stands for the number of meters in 1 kilometer. So there are 1,000 meters per kilometer, which is why we've multiplied by 1,000. If you see seconds divided by hour, that stands for the number of seconds per hour. So there are 60 seconds in a minute, 60 minutes in an hour, so there are 3,600 seconds in 1 hour. So what that means is there's 1 over 3,600 hours per second. And I'll explain to you why we flipped it over now. So the reason we multiply by the number of meters in a kilometer is we were trying to cancel out the kilometers as part of the unit. So to start with, the unit is kilometers per hour. By multiplying by meters per kilometer, that has now become meters per hour. By multiplying by the number of hours per second, it finally becomes meters per second, which is the unit that we want there. So that's how I chose which way round to multiply the numbers that we've got. So if we want to get the distance travelled, we take the speed in meters per second, so 2.7 blah, 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 times it by the time, 60 seconds, and that gives us a distance travelled of 167 meters in that time of 60 seconds. Okay, so that's when the speed is constant. What about when the speed changes? So this next one, we've got a car starting its journey travelling at 0 meters per second. So we can see that on the graph at time 0, speed is 0. It ends its journey 30 seconds later at a speed of 15, so we know it's going to pass through the point 30, 15. And it says the acceleration is constant, and we want to calculate the distance travelled. So if acceleration is constant, that tells us that this graph is a straight line, because the gradient of a straight line is constant, and acceleration is the gradient of this graph. So we can see that the area between the graph and the time axis is a triangle in this case. So the area of a triangle is half times base times height. The height is the speed, the final speed, which was 15. The time was 30 seconds. So we're going to do half times 15 times 30 gives us 225 meters traveled. Okay, so we're going to look at one last example. So what if it didn't start at 0 meters per second? What if it started at 5 meters per second? It traveled for 10 seconds and finished at 10 meters per second, and again acceleration is constant. So this time we've started the graph at 0.5 because it's going at 5 meters per second to start with. It still finishes at 10 meters per second, and it's still a straight line because acceleration is constant. But now we've got a shape which is a little bit more complicated to get the area of. So first off, I'm going to split the shape into two. So you can see I've split it into a rectangle and a triangle. So we want the area of those two added together. So the area of the rectangle is 5 times 10. The area of the triangle is 5 times 10 times a half. So that gives us a total distance traveled of 75 meters there. And it doesn't matter how complicated the area under the graph gets, all we do is split it up into shapes that we can easily calculate the area of, so rectangles and triangles, and we can get a good idea of the area under a graph. Okay, so that's how we get distance from a speed versus time graph. Let's now look at describing the motion of objects using a speed versus time graph. So this is the first graph we looked at, and the graph is the red line. So you can see that speed stays the same the whole time. So we would describe that as saying the object is traveling at constant speed. And if speed stays the same, that means acceleration is 0, because the change in speed is 0 over the time. And that means the gradient of the graph is 0, which is why it's a horizontal line. That means it has a gradient of 0. And we know this object is going to travel a total distance of the speed times the time, depending on what those values are. So that would describe the motion of the object from the graph there. Let's have a look at this graph that we finished with and how we describe this one. So we can see that it starts at a speed of 5 meters per second. So that would be our starting point describing its motion. We can see that it experiences constant acceleration because the graph is a straight line. And we can actually calculate what the acceleration is using the change in speed divided by the time taken. So the change in speed is 5, time taken is 10, so we can see the acceleration is 0.5 meters per second squared. We can see it finishes at 10 meters per second after 10 seconds. So that's the next thing I describe about its motion. As we just calculated, we know it travels a total distance of 75 meters in that time. So we've really fully described the motion of this object over those 10 seconds. The last one we're going to describe is this graph here, which is not a straight line. So it's about as complicated as it's going to get. So we can see it starts at a speed of 2 meters per second. And we can see it is accelerating because the speed is increasing. But the acceleration is actually increasing over time because we can see the gradient of the graph is increasing over time. So therefore the acceleration is increasing over time. And we end up after 20 seconds with a speed of 10 meters per second there. So if we wanted to find the distance traveled, that would be quite tricky here because we're going to split it up into lots of little shapes to try and get that area. We could do it, but I'm not going to do it now because it would take longer than necessary, and honestly, I don't think it's worth it. So That finishes off this video describing the motion of objects from speed versus time graphs. I hope you found this video useful to learn some of the basics about the motion graphs. If you have any questions, please feel free to comment on this video and ask. I'll try and get back to you as quick as I can, but thank you very much for taking the time to watch.